Okay, so we are discussing the derivation of numerical aperture of optical fibers. So for that part, let's consider an optical fiber who's having uh, one core of refractive index n1 and one cladding of refractive index n2. And let us consider a light from the air medium is launched. So uh, here it is said, let a ray of light A and B is launched from air medium with refractive index n naught. Okay, and this n naught is lesser, the refractive index n naught is lesser than n2, and n2 is lesser than n1. And let us make consider that it makes an angle alpha of the axis with this AB ray makes an angle alpha with this fiber axis. So this angle, if it makes a critical angle over this core cladding interface, then it is this angle is called the acceptance angle of the fiber. So this is alpha is the acceptance angle. This alpha also makes a cone which is called acceptance cone. If we consider a total 2 alpha angle and make a cone, then that too will be calling as acceptance cone. Okay, so this incident ray propagates inside the fiber and gets reflected completely by core cladding interface. Now if angle is this alpha is such a way that this angle, critical angle, is the angle of incident here in core cladding's interface is greater than this critical angle, then light will be reflected back. If that is so, then we'll be having a propagation of the light inside this fiber. So if the angle of incidence is yes, according to Snell's law, the incident and refracted ray propagated in the same plane, you know, the incident ray and propagated ray are should be in the same plane. This is the plane. So hence, on applying the Snell's law in AR and core interface, so then what we have, we from the Snell's law we can find n naught is sine of alpha is equal to n1 sine of theta. This is angle theta. uh, then from the above figure we can write theta equals to pi by 2 minus theta c. Now this is theta c, and there are two parallel lines which are cut by BC ray. So what this angle will be make from the surface to this normal, that will be definitely a 90-degree angle, and this part of this angle, this angle will be equal to this theta. So what will be the theta c? Theta c will be the 90-degree minus this sorry, theta will be 90-degree minus this theta c, definitely. So if we put this part, this pi by 2 minus theta c in this the value of theta in equation 1, what we'll get? We'll get n naught sine alpha equal to n1 sine into angle pi by 2 minus theta c. Now sine 90 minus theta c is equals to cos theta c. This is a trigonometric identity. So from here we can get from this equation, if we take n naught to that part, then from this cross multiplication we can get n1 by n naught into cos theta c. So since we know that cos theta is equals to under square 1 minus sine square theta, so this is also another trigonometric identity from where we can keep it. Now we apply the Snell's law at the core cladding interface here in this surface. If this is core, this is cladding, if we apply this the Snell's law at here, then it says that n1 n1. What is n1? N1 is the uh, refractive index of this core. N1 theta c will be equal to n2 sine of pi by 2. Okay, so from here, since sine pi by 2 equal to 1, so n1 sine theta c will be n2. So from here, what will be the sine theta c is nothing but n2 by n1. Now what we'll do, we'll put this sine theta c, the value of sine theta c, that is n2 by n1, at in equation 4. So that will be giving us the value of cos theta c, which will be under square 1 minus n2 by n1's whole square. Okay, now this value of cos theta c will be applying in equation 3. What was there in equation 3? Equation 3 says sine alpha is equal to n1 by n0 into cos theta c. So in place of cos theta c, we will be applying the value of this cos theta c. Okay, that gives us this relation sine alpha equal to n1 by n0 into under square 1 minus n2 by n1 whole square. Now if we take this part n1 by n0 inside, then it gives me this relation. From this relation, what we will do, we multiply this part with each of this under each element of this bracket. So that will be giving us a relation which is equal to n1 by n0 whole square into n1 n2 by n0 n1 whole square. From here, n1 n1 will be cancelled out, so and that will be n1 square by n0 square, that will be n2 square by n0 square. So we took n0 common, then we have got n1 square minus n2 square by n0 square, that will be under root square. So now what was n0? N0 was nothing but the refractive index of the air medium, and we know refractive index of air medium is almost 1. It's actually 1.00029, which is we can consider as 1. So this part will be becoming 1, so that will be sine alpha, which will be equal to under square n1 square minus n2 square. So by the definition, we already talked about how to find this numerical aperture. The numerical aperture can be expressed as sine of the acceptance angle. So sine of the acceptance angle was alpha. So sine of alpha is now become under square n1 square minus n2 square. So the equation 9 is the expression for the numerical aperture of the optical fiber. So higher the value of Na, greater is the light directing ability. How it can be made efficient? If n1 is very high, n2 is very low, then their difference will be making a very great, very efficient numerical aperture. However, the greater value of Na can be achieved when difference between two refractive indices is high. Okay, so this way uh, the angle of acceptance is calculated, is derived, and I am giving you some numerical problem on this numerical aperture to do. You will be practicing this numerical problems at your home, and with this I will be ending this class, and in the next class we will be discussing the types of optical fibers and advantages and applications of optical fibers. That will be the last class. And I'm ending it here at this point. I hope you will be doing this numerical problems, and will be showing me in the next class. Okay, uh, so I wish you I wish you will be staying at home, be safe, and we'll be meeting physically soon. Okay, take care.